In this video, we're going to go through calculating the equilibrium constant. So in this video, we're going to talk about how to solve for equilibrium concentrations when you have a balanced chemical reaction, you have your equilibrium constant, and then you have initial concentrations. So that's before the equation or the reaction has reached equilibrium. And we're going to use the Rice table method to organize the information and to solve for unknown equilibrium values. So here's our first example. It says, consider the reaction. So we have x plus 3y is at equilibrium with 2z. It says the initial concentrations of x and y are 1.5 molar and 2.0 molar respectively. And at equilibrium, the concentration of z is 0.3 molar. Determine the equilibrium constant. So let's start by organizing our information into what's called a Rice table. So I'm going to quickly draw this. All right, so R stands for reaction. So I'm going to put all of the pieces of our reaction. So we had X, we had Y, and we had Z. And it told us the initial concentrations of X and Y. X was 1.5 and Y was 2.0. Before our reaction has started, we know that Z is 0. Nothing has been made yet. And we know that Z at equilibrium is 0.3. That's it. That's all we know. So if we go back to our reaction, we know that we have a 2 in front of our Z. So Z is going to go up by some amount. We'll call that X. But it's going to go up by an amount of 2x because we have a 2 in front of it. So we don't know what it's going up by, but we know that x is some number, but it's going up by 2x. Okay. We know that x is going to go down because it's a reactant by some factor of x, and it's going down by x because there is no coefficient on x. For y, it's going to go down by a factor of 3x. Okay, so those are our change values. E is what the concentrations are at equilibrium. So our initial concentration, 1.5, minus x will be our equilibrium concentration for x. Y will be 2 minus 3x. So here, we know that 0 plus 2x is going to be equal to 0.3. So 2x is equal to 0.3. So we have enough information here to solve for x. So if I divide both sides by 2, x is going to be equal to 0.15. So now I can go back and solve for all of my other values. So 1.5 minus 0.15, and then 2 minus 3 times 0.15. We would get, for our first value here, we would get 1.35. And for y, our equilibrium concentration would be 1.55. So the question was asking us to solve for Kc. And we're going to write out our equilibrium expression. It's always products over reactants. So it would be the concentration of Z squared. Then we would have X. And then we would have y. Y is going to be cubed here. So we can just plug in all of our values. So z was equal to 0.3. And it's being squared. X's value, right here, is 1.35. And y's value was 1.55. And that's being cubed. So we plug this into our calculator carefully, and we get an answer of 0.0295 as our KC value. Okay, so in this first example, we were given numbers, and we were able to use those numbers, our initial concentrations, in one of our equilibrium concentrations to find the missing values for our equilibrium concentrations, and then we plugged in to solve for our Kc, our equilibrium constant. All right, let's look at another example. It says, consider the reaction. So we have a to the second, b to the second, or b2, is at equilibrium with 2ab. We're given the equilibrium constant here, and then we're given 2 of the equilibrium concentrations. So it wants us to solve here. All right, so let's start with the Rice table. We'll plug in the information that we have. So we have A, we have B, and we have AB. And we know that A is 1, B is 1.5, AB at our initial concentration will be 0, and that's it. That's all the information that we have. Well, if we go back to our equation, we know that A and B are both going to go down by a factor of x. We don't know what that is, but we know that they're going down by some factor x. AB is going to go up by a factor of 2x. Okay, so now we're just going to combine our I and C rows. So 1 minus x, 1.5 minus x, and then 2x. Okay, so now let's write out our equilibrium expression. So we know that our Kc value is 4.2 times 10 to the second, or minus 2. Products over reactants, so we're going to have 2x squared over, we're going to have 1 minus x, 1.5 minus x. All right. This looks really terrible. Really terrible. Yeah, so we can make an assumption here, or we can attempt to make an assumption here, to make this really simple. So we're going to do 2 examples. The first one will not be simple, so the one that we're doing is going to be pretty terrible. I'll show you the assumption that we can make. We'll test it. It's not going to work. The second example that we're going to do is going to be much easier. So if you're watching this and you're like, oh my gosh, this is terrible, oh my geez, what do I do? Just hang tight, okay? Because there is an easier way that you can do these types of problems where it's going to be a lot easier, okay? So just bear with me. So since this value is very small, we can assume that our x is going to be very small compared to the initial concentration. So instead of it being 1 minus x, if x is going to be a really small number, 1 minus a really small number will basically be 1, and 1.5 minus a really small number will basically be 1.5. So we assume that 1 minus x and 1.5 minus x will just be the same number without the x. Okay, so if we solve this using that assumption, this looks a lot cleaner. So it'll just be 1 and 1.5. Okay, so this is a lot easier to solve, so I would need to multiply both sides by that, divide by 2, take the square root, and you get x is equal to 0.125. Okay. So once you get to this point, you have to test to make sure that your assumption was valid. So I'm going to take my x and I'm going to put it over one of my initial concentrations. So if I take 0.125 and I put it over my initial concentration of 1 and then multiply it by 100, I get 12.5. So it's 12.5% of our initial concentration. So if it's greater than 5%, then you are in trouble, because then you can't make that assumption and you have to solve this using the quadratic formula, and it's very messy. Okay, so if we go back to this and solve it using the quadratic formula, you would obviously have to FOIL out the bottom and multiply that over. It gets really messy, but you basically end up with a quadratic. So your quadratic would look like this. Oops, I got to combine like terms. I missed a step here. Okay, so you'll get a really nasty quadratic. Make sure you combine like terms. Okay, so you would plug this into the quadratic formula, opposite b plus or minus the square root of b squared minus 4ac. So this would be your a term. This would be your b term. This would be your c term. The a term is always your x squared, b is always your x, and then c is always your constant. The quadratic formula is opposite b plus or minus the square root of b squared minus 4ac all over 2a. So I plug everything in and I get x is equal to opposite b. So it would be, let's see, our coefficient would be 0.105 plus or minus the square root b squared. So 0.105 minus 4. A is 3.958. C is negative 0.063. All over 2A. Okay. So I plug this all in. You have to be careful. You're going to get two roots because you are doing plus and minus here. You only want to end up with a positive root. Okay. X has to be positive, so you get a value of x is equal to 0.114 molar. Then you would go back in, take your x value, go back up, and substitute it in here. So if you do that, for A, you would get 0.886. For B, you would get 1.386. And then 0.228. That's terrible. And I didn't even do all the work here. That's absolutely terrible. Okay, so fortunately, there is an easier way to do that, and we're going to look at that method in this last problem here. So it's very similar. All the concentrations are given. So let's begin by setting up our rice table. majority of the time, you will find that this assumption works. Okay, so our initial concentration, let's hit the right tool here, 0.8. This is all given in the question. Okay, so we know that our C₂H₄ and our H₂ and our C₂H₆, all a factor of 1. So going to go down, going to go up. Again, in the question, we are given a Kc value, so we're going to set it up just like the last one. So our Kc value is going to be equal to x over 0.8 minus x, 1.2 minus x. So we're going to make that same assumption here. So if we make that same assumption that x is a very, very small value in the denominator, it's going to be insignificant. So we can rewrite this now. We only do that for the denominator. That's what we get. Okay? So if we solve here, you will get a value of x equals 0.00115. And I can already tell you that if I plug this into my initial concentration, it's going to be much less than 5%. So our assumption here is valid. So because it's much less than 5%, I can use that. So for my equilibrium values, I would go ahead and solve for those now that we have x. So if I do that, I will end up with, for C₂H₄, my value, I would solve and it would be 0.8 minus 0.00115. I get 0.79885. I would do the same for H₂. I get 1.19885. And for the last, C₂H₆, I get 0.00115. And that's it. That's it. Yeah, that was a lot. So just pray when you're working these problems that you're able to make that assumption and you don't end up with something like this. But I would definitely practice the quadratic formula just in case, because you never know what AP is going to throw at you.